awry, but this is going to be a real brief one. But I wanted to walk through everything here in terms of a brief history of MODFLOW, all the different versions of MODFLOW that are out there. And the main reason I want to do this is starting October 14th, we have the training with Jim Rumbaugh for transport. And he's going to run through how to do transport with a bunch of different versions of MODFLOW. So I thought we better at least talk about what the different versions of MODFLOW are in advance of that. So you have a little bit of background going into that. There will be a little hand waving. I'm going to show a couple graphics. Add your photo. It'll help people get to know you. That's interesting. Oh, my Skype account. Okay. This always bothers me because if I get a phone call, that's why.
We'll just sign out.
Open up. So I am going to sign out here. Goodbye. Okay. So the first versions of MODFLOW that we ran were MODFLOW 2000. If you ever open up the Mahomet Aquifer model, and I think George is going to talk about that the next time he runs one of these sessions. Last time he went through the geology of the Mahomet, is that correct?
He went through.
Did he bore you that much?
Yeah. Last time
Yeah.
he did the geology of the Mahomet and began talking about model creation of the Mahomet.
Okay.
But we didn't get too far with regard to that discussion.
So he hasn't actually,
geology.
he hasn't opened up the model itself yet?
No.
Okay. When he does that, it's going to be developed in MODFLOW 2000. And again, it's important to distinguish MODFLOW itself from a graphical user interface. When you're opening up the model like we talked about on Tuesday in Groundwater Vistas, that's the graphical user interface. And it's pointing to a version of MODFLOW, and you can control that. And then within Groundwater Vistas, you can set all the properties for all these different versions. So this is our online guide to MODFLOW 2000. This is what the Mahomet Aquifer model will be built in. This is really just some minor improvements on MODFLOW 88, which was an earlier version of MODFLOW. Nothing big changed. You can almost just view this as original MODFLOW. When you go onto this website and you look at the list, they don't even bother giving you a guide for 88. They don't even bother pointing you to it. It's probably somewhere, but most people are going to jump right to 2000. And there's not much added there. This is your standard well package, rivers, drains, all those things. You're going to see those carry through all the way through MODFLOW. So if you're interested then in just kind of understanding the inner workings of MODFLOW, and I just recommend doing this slowly through time, reading through some of this documentation is worthwhile. So to find this, you can just type in online guide to MODFLOW 2000, maybe USGS, and that'll take you to this page. You can also look at the documentation. When you download Groundwater Vistas, it has all of this documentation as well. And it'll walk you through a number of questions. How do you want to install it? Where can I get it? What have you? Actually, this is an interesting one. One thing we want to start doing is archiving our models. It's always a good idea. And when you do that, you should archive the executable file. And so you can download from the MODFLOW webpage. You can just type in MODFLOW. It'll bring up a USGS page, and you can download any version, the newest versions of MODFLOW. Any of these old versions, you can download those. And then point Groundwater Vistas to that version. There's more to it because you have to adjust properties, but that's the basic idea. Or if you're in GMS, same thing, you can do that, and then just run that version of MODFLOW. But this gives you a lot of nice material. Frequently asked questions, certainly what is conductance, which is what we assign to river cells. There's the math behind it. And it will give you some important references here to go to. So certainly when you're going through and you have a question about MODFLOW, feel free to come ask any of us, but also this is a nice reference. My model hasn't converged. What can I do? Well, you saw one of the things we can do is in groundwater vistas, we can check a box that forces convergence, whether it's actually converged or not. But there's some other recommendations here that you may find useful in modeling. Transient models make shorter time steps. We'll actually see this when we're working in the big model and we start going from annual to monthly time steps. Stress periods, we'll actually see the model actually seems to speed up a little bit. Whole host of other things. Don't really want to get into any more details than that at this point on basic MODFLOW. You can have this at your leisure to look through, but this is useful. Since this is up here, see if anybody knows the answer to this. You build a model grid, it has a boundary. You give it a finite area, right? In the big model, it's the southern boundary is halfway through Illinois and the northern boundary is up in Wisconsin. So when you get to the edge of a model, is the edge of the grid a no-flow boundary? What do you think? I see thumbs up. That you're saying yay on that?
That's my guess.
Yeah. That's a detailed explanation. I was really hoping for more than that. I'm doing this completely raw here. So, but it is, and that's an important thing to remember, that your model is not, it doesn't have finite boundaries. And so if you're developing a model of a very local area and you don't have boundary conditions in the model, you're going to put fictitious boundaries in, fictitious no-flow boundaries. You're treating it like, oop, water's not going to go in and out of here. And if that's not true, then you built a bad model. It's a very common mistake in models. And that's why our model stretches so far to the south, so far to the east, so far to the west. So when we go into East St. Louis, the other model that a lot of you have seen, the Mississippi River is a boundary, and then the Bluff is a boundary. And the model domain covers those, extends over that area. Green River lowlands, Mississippi River is going to be a boundary. Rock River is kind of a boundary. Yeah, and then some of it is just where the sand coating ends. And then there's also that weird spot of, you know, if you cut a model off too soon, are you actually getting recharge coming from the northeastern part of the model domain. So it's very important to consider that in your conceptual model. In the conceptual model, I have a layer that pinches out. How can I simulate that in MODFLOW? We've talked about pinch outs, and we just go to unstructured grid, which means we just pinch it out.
This is an FAQ sheet from MODFLOW 2000.
This is all MODFLOW 2000.
Right.
Yeah.
Does MODFLOW 2000 have unstructured grid?
It does not.
So that's why
it's its own thing.
Yeah.
but you're going to notice something as we go through these. But I actually just stopped here because I've never even heard of this package. The HUF2 package apparently allows you to do layer pinch out in MODFLOW 2000. In MODFLOW 6, you can also pinch out a layer. But in MODFLOW 2000, which is what this FAQ is about, you normally can't, but apparently, yeah, you can using this hydrogeologic unit flow package. Okay, I don't know if that's something that's supported in Vistas, but it's something that's out there. Didn't even have an idea it existed. So, interesting. And that's why it's good to poke around this. I've obviously not, and I'm learning things as well. And then how do you simulate solute transport with MODFLOW? So this is important, like when you're importing in your data, you can import in heads, you can import in drawdown, you can import in flow. Groundwater Vistas gives you the option to import in concentration, but concentration isn't something MODFLOW does, it's something that you have to have a separate package to do. And that package is MT3DMS or MT3D USGS. And that is what the training that Jim Rumbaugh is going to give, starting on the 14th, is going to cover. He's going to cover these two things. He's going to cover a whole lot more too. Okay, any questions on this? You can go down through here. This tells you which packages work together and which ones don't. So if we wanted to try HUF2, what is the legend here? It doesn't have a legend. I'm assuming it has a legend here. Once you figure out the legend, you can test. This has me concerned though that HUF2 may work with some packages, but it doesn't make sense that it wouldn't work with some of these. So I'm not quite sure how to read this table, to be honest.
Well, no. Go back. So HUF2, when you get to that V, it's saying now you, instead of reading it vertical, you read it left to right, doesn't it? Because this, or are you on HFV6? Oh yeah, so yeah, anyway, you read that vertical column for those first items, and then if you go diagonal, you can read the rest of the options. So for reading HUF2, you can read the vertical column first to see what it's compatible with. And then when you get to the gray zone, you skip down one more row, and then all of the remainder across also fill out the bottom of, you see what I'm saying? Since it's a mirrored grid, they don't have to, they'd be duplicating the values.
So what are these letters?
I don't know what the letters are.
I refer to the letters at the bottom of the page.
It does?
Oh yeah, there you go. The rules governing incompatibility. So when it's been,
Oh, there we go. There we go. Okay, I'm just kind of curious here, like HUF2A. Oh, I got it. Okay. HUF2 is a replacement for BCF or LPF. And those packages themselves, if you're curious what those are, block center flow package. It's used to specify properties controlling flow between cells. A similar package is LPF, but they're replacements for one another. And so LPF, again, used to specify properties. There's some differences here between them, and some of them have to do with which solvers they interact with. LPF is a newer version. HUF2, honestly, I've never heard of anybody using. I don't know if that's brand new or just something that was really old and not really used that often. But then the other nice thing is that Groundwater Vistas takes a lot of this out of your hands. You don't have to worry about what's in the LPF file. But if you're not using Vistas, you're not using a GUI, and you're trying to figure out what one of these files actually is, when you read through it, this tells you everything that's defined within it. And so I wish I would have brought a version of the LPF package, but an LPF file, wish I had an example here. But you can go through line by line and see what everything means. So within it, you're going to be defining a flag and a unit number. And so unit numbers are just where MODFLOW is writing the flow. And you can define that in the GUI, but you can also define it directly in this LPF file. Or you can use FlowPy to, translate. So when you use FlowPy and you're defining the LPF, you'll actually be going through. And if you need to set, I don't want to write my cell-by-cell flow terms, that'll be an option in your Python code. These other things will be an option. So if your model doesn't work or you need it to do something else, go into this data and you can modify the code that you already have and say, oh, sometimes this will default. So you go through, and if it's defaulting to 0, you may say, no, I want to write it. And so you can put greater than 0. So this is something that, honestly, the best way to learn this is to take a model, open up something like an LPF file, and dive in and just look at and compare it. That's the best way to learn at that point. And then you can scroll down through here. Let's see if we can find something that's a little. Let's do one that's a little more, makes a little more sense. I accessed it through here, but you can also go here. These are the packages associated with MODFLOW 2000. Probably should have started here. Phase 6, a discretization package, zone package. Let's look at some of the boundary conditions. Specified flux. Yeah, we're going to be working with the well package. So same thing, this tells you all the details about the well package. This is where, of course, you assign your location, how much you're pumping, and you can go through and see what all these different parameters are. And here's some, that other stuff is sort of preamble stuff. A lot of that's just defaulted. But here's where you start to get to important stuff, where you're going to define the number of parameters and whether well data is going to be reused. That's interesting. You learn things through this. I've always skipped over this and I always jump down here because this is what you're really working with in most models. And that's where your layer is, where your row is, where your column is, how much you're pumping. And I believe you can probably assign an XYZ instead of a row layer column. This is an optional argument. You'll find those popping up as well. You have to go back to item 2 to understand this. So it's a bit of an experience going through this stuff. But But if we're developing a well package from scratch, we're just appending on a bunch of these row layer columns into our well file. And then solvers, there's a whole host of solvers you can use. We've generally used PCG. And you can really dive in pretty deep into solver theory. One of the things that, this one's easier to understand than the others because you have to assign a head change criteria to your solver. And you'll see all of this in Groundwater Vistas, has all these same options. Head close, residual close, is basically flow cubic length per time. And a number of other nuanced things, a relaxation parameter, a damping factor. We adjust these things to get the model to converge better. Okay. Yeah.
How can I choose which package for the solvers we use in a particular like specific questions?
I'm sorry, could you repeat that?
How can we choose like which package to use for a specific problem to solve?
Oh yeah, that will be based on your name file. And so the name file is where you define your different types of files to point to. So when you run groundwater, when you run a model, it'll create a name file. And within that name file, it will include a line that points to a list file and a line that points to a well file or recharge, river, drain, and then a line that points to a solver file. So if you want to run PCG, then you're going to put a PCG file and point that in the name file. So if you wanted to test out different solvers, you can actually have the same model and then just vary PCG, or you can use SIP for these different solvers just by changing that in the name file and then rerunning the model. And you'll get a different solution if you're using a different solver. Hopefully it won't be too variable. So that's the way you change it if you're developing all of this by hand. If you're developing all of this with FlowPy, then there's a similar documentation. Which you may already be familiar with, but I should call this up. So who's seen this? Okay. So this is where you can get that same information. Through the FlowPy resources. Improve this a little bit. They didn't have tutorials last time I looked. There we go. If we wanted to run the PCG solver, then you would use this module to define your PCG. Just put that in your code and set this up to run PCG or set this up to run what have you. But you know, this is handy that we talk about this because let me go back to the tutorials. This is brand new. I had never seen this before. This is what Shelby put into a Jupyter notebook. I've gone and scooped her. There we go. So it's actually pretty simple. I'm going to jump ahead a little bit with FlowPy, but you know, it's still relevant that you create your model object. And where do we create our model object here? Defining paths.
Right there. MF.
Yeah, right here. So once you've created your model object, you then go through and run this module pointing to that object. And you do that for the solver or discretization or any of these other properties. So where did they? There we go. So if you wanted to run SIT, then you would just simply make this MODFLOW SIT or whatever the appropriate one. So just that simple then to change the solvers. If you want to know which solvers you have as an option, you can go back to that original MODFLOW.
Do we have a rule of thumb, like when we are first running the model, so which solver should we use, like SOR or PCG or
Which version of MODFLOW are you running?
like MODFLOW 6 or 75?
So if you're using MODFLOW 6, it's a whole different set of solvers. And that's something that we just kind of use whatever is defaulted to start with. We've not gotten to the point we've explored deep into the different solver settings. But I don't know that there's actually a whole lot of options when you get to MODFLOW 6. So we'll come back to that. Any more questions on MODFLOW 2000? I started there because that one's one that we've used a lot, but really we're moving away from it. I'm going to close out of that. MODFLOW 2005 is very similar to MODFLOW 2000. I think that's all you need to know about it. MODFLOW NWT, well, okay. MODFLOW LGR lets you, that's a local grid refinement. So it lets you kind of zoom in on your model. Different GUIs support that at different levels. MODFLOW CFP introduced conduit flow into the model. So if you actually want to simulate karst settings, flows through pipes, you can do that with CFP. MODFLOW NWT introduced a way to get around a major issue in MODFLOW dry cells. And I'm going to leave most of the dry cell discussion to George. He'll go on his rants with dry cells. But as soon as this actually try refreshing this.
Install the PDF.
I guess just frustrating. There we go. So here's the issue that we run into all the time with modeling. And I'm just throwing this up just so you understand why they've changed, made some pretty substantial changes to MODFLOW. This is really the only major change they've ever made. If you look at the McHenry County model, which I'm happy to share with you. The way it's currently written, it's in MODFLOW 2005, and it doesn't use NWT. So MODFLOW NWT is a version of MODFLOW 2005 that's designed specifically to treat dry cells. So everything purple here is a dry cell. You see the water table. When this model runs, all these cells here are going dry, and sometimes it's okay, but it creates a lot of numerical issues. MODFLOW doesn't handle this very well. The cell is dry, it wants flow to go through, it doesn't quite know how to get flow to go through. It figures it out most of the time, but it takes a lot of computational energy to do it. Your model's going to run really slow if you have a lot of dry cells. It's a lot of work for it to figure out this water table down here. And of course, you see the big problem occurs right here. So what happens is that your cell on the surface goes dry. In reality, it should be dry. There's no water in that layer. And then the recharge is assigned to go to the top active layer. So if that cell goes dry, the recharge goes down to the next layer. But what if the next layer is an octocharge and you're assigning a lot of recharge? So we've talked a little bit about drain cells, and if we throw drain cells over the entire model so that we can throw whatever recharge we want on and control the head. Well, this cell's dry. Even if there's a drain cell there, it's not going to honor it. And you get this massive spike in the head to where, because recharge has been assigned to a very low permeable material, and it just bounds up, and it's only at that cell. And our McHenry County model has probably 30, 40 little spikes all throughout it because this happened. MODFLOW NWT goes in, and you're going to notice that the cells here aren't actually dry. They're given a little bit of a thickness. And what's happening, the difference is that it's gone from this model to this model. So honestly, I don't know why that spike's up there and not there. That's a mistake. But it's taken the cell that went dry and it's kept a small fictitious amount of water in it. It just has a little bit of water that it maintains there. And then when this starts to spike up, there's a head here. It's not just removed from the simulation like it is up here. And it says, wait a minute, no, the head here is at the bottom of the cell because it's almost dry. And when it tries to spike it up, it can actually go back into the calculation and say, that doesn't make sense, and it controls the head. And it keeps it low. And so it's a numerical trick is what it is. And if you're interested in the details of it, that's what this paper is about. These are two very well-respected researchers in Wisconsin, Randy Hunt and Daniel Feinstein, and this is their review of MODFLOW NWT. This was an article in Groundwater a few years ago where they discussed the benefits of MODFLOW NWT. So the reason I'm harping on this is twofold. You'll hear George call this voodoo. It's kind of voodoo. There's mathematical basis behind it. But it also led, and the reason George correctly calls it that, it led to a lot of misunderstanding in the community. People misused this and didn't explain it right, is some tricks that we'll find out later, much later, when we talk about multi-aquifer wells, and it doesn't handle those properly. Or it handles them properly, but it does them in a different way. And if you think, long story short, it kicks out pumpage in these cells that kind of stay dry. We just saw a cell that technically was dry but kept a fictitious thickness in it, it kicks out pumpage in a different way. So if you're looking for dry well flow loss, you have to look at it in a different way. Because if you have a cell go dry and a well is in it, you lose all that flow from your model, which is always a problem. It's flow that's there in reality. So you don't want that to happen. It would be like if half the cells were dry in the Green Earth or lowlands and kicked out half the pumpage in there. Well, we know that pumpage is actually there. So that's why this is really important. Now from MODFLOW, and you can read through all this, it's a lot of the same packages. The big difference that I should point out, since we're talking about solvers, is that, well, the solver is still, PCG is still an option. I actually think this is a bit incorrect. It's a much different solver that's being used. So this is actually incorrect here. That's the solver, that you can't use PCG with that.
Something new solver.
Hmm?
The new solver.
Yeah, thank you. That's the solver I was hunting for. This is your solver you're using with NWT. Why they have, this is a mistake on their part. Those are not options with NWT. It's a very sophisticated solver. It's actually a sparse matrix solver. Anybody know or care about solvers? It's, okay, well, I can't really explain PCG that well to you. But a sparse matrix solver just basically tries to keep most of the elements along the diagonal. And it runs quicker, it's a little more stable than old PCG, is what we find. And it also allows for you to turn on upstream weighting. And upstream weighting is what I was just talking about. It's basically the way it works. You have MODFLOW 2005, that's your standard version of MODFLOW. You turn on upstream weighting and now you're running in WT. Is a rough way to say that. And so upstream weighting is putting that fictitious thickness in, basically what that's doing, to keep cells from going dry. But this is your solver. Immediately notice it's not just 6 options. It's head tolerance and flux tolerance, those are still the same. All sorts of other fun little solvers, back tolerance, back reduce, and these things do matter. You get in the groundwater this system, there's a simple, complex, moderate. MODFLOW has those options as well. And we always start there, but sometimes we have to continue tweaking. And I will admit, we don't have as good a grasp on this solver as we should. And there's periodically a training by Mr. Sorat Pandey, who was heavily involved in developing this code on solver settings and never been able to get to that. So that's probably in the works in the future, where I'm going to hunt for a couple people, hopefully myself, to be able to go with that. Or it may even just be in office kind of thing. Last time I was gone and Devin was gone, and so it never materialized the last time we had this training. But we really need to have a better grasp of these solver settings. But we know some of them, and you can dive in, and it gives you a little bit of an explanation here, right? But head tolerance, the max head change between outer iterations for the solution. So finite difference, it's iterating through your solution, and it's looking to see what is the most the head change between those iterations. Flux tolerance, this is the same thing as the residual, more or less. The maximum number of iterations that you can allow, that's one that if you really want a very fine tolerance on your model, you run it for 1,000 iterations and you let it, you have a very small convergence criterion, just let it keep running if you really want to do that. Portion of the cell thickness used for smoothing, adjusting storage, and conductance connect. I don't know. So on and so forth. I don't know what all of these are doing. This XMD solver is another level of solver complexity that you can activate. So this is just, how are you solving this matrix? It's a solver within a solver, basically. It's complicated. I can sit here and keep babbling on about how complicated it is. It's complicated, and we need to get a better feel. We need to understand what it means when we're changing gamma. We can read this, but what does this actually mean? We almost need to go through and do some tests and whatnot. So that would be a good FlowPy exercise or Groundwater Vistas exercise, what have you. Oh, when I do this, this is what happens. When I do that, that's what happens. Honestly, right now with our big model, it's that's kind of it. It was, if I increase this, does my model get a little faster? We need to have a better understanding of that. So yeah, this is though if you're using NWT. So okay, that's MODFLOW NWT. And so next, I guess 2 weeks from now, when Jim gives his tutorial, he's going to talk about MT3D, which is the contaminant transport package, that after you run the model, after you get a flow solution, you feed that into MT3D, and it will run the solute transport once it knows directions of flow, and then it can calculate advection, it can calculate dispersion, all that stuff that you can do once you have the flow. And at that point, that's it. MODFLOW MT3D MS, or he'll also talk about MODFLOW US or MT3D USGS, I believe he calls it. It's just an updated version of MT3D, but they all tie to these codes. So the problem becomes, we've moved past those codes. I still wanted to walk through this because some things like the river package and the drain package, they don't change. This is still the best resource to understand those. But we've moved on to unstructured grid, which isn't on here. It's not even documented on the USGS website. Yet another reason we want to get away from it. Unstructured grid was developed separate from the USGS. USGS fell onto some hard times with funding. With NWT, they were moving towards some things where they, once they had this simulation that does a sparse matrix solver and all that, then they can actually start looking at local grid refinement, but it's not an officially sanctioned USGS version of MODFLOW. And yet it's in our GUIs, and that's the one we're using. So if you actually type in MODFLOW unstructured grid, it doesn't end up on their page with a nice tutorial. You can still get some documentation here from it and read up on all of that. It's the same basic idea with the solver. It does the same thing with dry cells that NWT does. It does the same thing with most most other processes, with the addition of being able to build a nested grid and zoom in locally on an area. And I still think when we talk East St. Louis, it's going to be really important that we can do that. Zoom in locally so we can do a rainy well analysis. I guess it's optional to use Newton-Raphson. I've never seen anybody not use it. I actually tried it once because George is, let's just say, skeptical of Newton-Raphson because of some bad science he's seen. I still contend the code is fine. It's the application of the code that was flawed. But this gets into that whole discussion that we had about vetting these things, because this is a great example, not exactly a sanctioned USGS code. It is, it's on the USGS website, but no support for it through the USGS. It's supported by SORAF, who I mentioned earlier, very bright, understands these solvers inside and out. And it's documented and it's supported. GUI developers love it. So I just bring this up because one of the things that Jim is going to discuss, because Jim Rumbaugh is very much a supporter of unstructured grid, he's going to talk about capabilities of unstructured grid to do its own solute transport, its own contaminant transport. So unlike MODFLOW, other versions of MODFLOW that require a separate MT3D package to run solute transport, kind of a post-processing, unstructured grid allows you to do some solute transport, allows you to assign the concentration within the unstructured grid code. It's not a separate code. And the GUI supports it. I'm going to assume GMS supports it as well. I'm not certain on that, but Groundwater Vistas allows you to assign concentrations and what have you. So you can do your entire contaminant transport here. And when I talk about not vetting anything, I simply know that it's possible. I've seen some people do it, and that's all I can say. We've not done it. We have no experience at it ourselves. But I think that's a real possibility for East St. Louis at the very least. If we go back to FlowPy, which I accidentally closed, there is some support for unstructured grid. I was not sure if there was or not. I think that's fading though, as they switch over to MODFLOW 6, which I'll talk about last.
Is the USGS the developers of FlowPy, or is it okay?
Yes, the USGS developed FlowPy. Actually, technically not true. It was from my background, analytic element modeler, who developed FlowPy, Mark Bacher, first developed it, then he passed it off to them. And they've been updating it. And they keep it all updated here. Not always perfectly, but it looks like they've made some big improvements. So here you actually see this BCT is unstructured grid transport. And DISU is discretization. So I'm assuming if you scroll down through here, we'd be able to add nested grids in the discretization file. But I don't know that for a fact, that there's support for that. But oh, that's a pretty big one. You can't do a multi-layer unstructured grid model in FlowPy. That's kind of a detriment. Most of our models are more than one layers. So that's a challenge. I'll just say from my understanding, there's not a lot of future for unstructured grid in the FlowPy environment. Okay. The other things, though, just before we move on from unstructured grid, that Jim Rumbaugh is going to talk about is geothermal flow, any kind of density difference, salinity gradients. Unstructured grid supports those things as well, and standard MODFLOW does not. And I think it's early November. Our colleague over at the Geologic Survey, Yufan Lin, for those of you who've met him, is very interested in geothermal. And he's going to come down and have a chat with Kevin O'Brien about potential geothermal research. So that's another reason we want to have this training to see how does this work in unstructured grid. Is that something that's actually a realistic goal or not? Then we talk about salinity gradients. There we're thinking maybe, Mount Simon, highly saline when it's upconing, and we see this sort of potential density gradient as the water upcones or whatever that is. We may need to account for density there. So unstructured grid has a lot of nice features. It's just generally to access them, we're going into the proprietary realm of groundwater vistas. Okay, and then the last one is MODFLOW 6. And what you're going to notice right away is that because MODFLOW 6 is still under development, we don't have the nice tutorial breakdown. We just have a PDF document. Devin also has, and maybe we're at the point that he can share those with us at a future session, and that walks through some of the specific things that MODFLOW 6 brings. But MODFLOW 6, in short, it still gives us the dry well flow loss capability. It gives us unstructured grids. It gives us the ability to treat two models as separate objects and run them in tandem and link them together. So we could have a local scale East St. Louis model and our large regional Illinois groundwater flow model, and we can link them together as two different objects and run them just like, you know, if I ran on my machine and Mike, you ran the other on your machine. Same idea, but we're running them kind of in tandem. They're linked together. There's some exchange of information between the two.
You can basically set the boundary conditions of the small model.
Yep, exactly. Yeah, so when George was talking about those local scale models, the traditional way is we just simply, we go into the Illinois groundwater flow model. Let's say we want to do Lockport and build a model for Lockport. We would go into what we have on the regional scale. It's 2,500 foot cells. We want 500 foot cells. We would just build a local model. And then when we pull that out, because our boundaries are no flows in that smaller model, we actually want to know the exchange. So we would pull out constant heads or constant fluxes based on the original simulation and use those in our boundary for our local scale model. Okay, now what if I want to update that? There's a lot of steps that we'd have to go through to update that. If we run the big model again, Now I got to pass that to the little model, but maybe the little model needs to change the big model. Big circular process that you don't have to worry about here because you run them in tandem as two different objects. So the big change in MODFLOW 6 is they wrote the code in object-oriented Fortran. That's tickling you for some reason.
It works, it works.
I just shrug. It's like, okay, whatever. But that's how they rewrote the code, made a lot of the MODFLOW community mad, because most of the MODFLOW community knows Fortran 95 or something, whatever it was originally written in. And we've not tested that functionality either. That's just what they said it can do. But it's very attractive for us to be able to build an East St. Louis model and a Lockport model, and just rather than going through all the steps of trying to get that in our big model with a refined grid and increasing run times in that big model, just simply run them all separate. Run our small model, it'll run quicker. That's the idea. So things change, the discretization package. Through all of this, it eventually goes away from layer, row, column, because if you have unstructured grid, it now has what's called a disv package, discretization by vertices. Because if you get an unstructured grid, you don't necessarily have a row, layer, column anymore. So everything's just designed by vertices. And that's unfortunate for people who want to use Excel. But when we get outside of Excel and get using Python to analyze everything, it's not a huge deal at that point. Handling of dry cells, just like Newt, just like unstructured grid. And you can read through this, there's quite a few differences. But at this point, I think that's best for us to first let you see the models that you're currently working with, and then after you get familiar with those, we'll have Devin run through. He went through a workshop on this, and they passed out a lot of PowerPoints and what have you that he can run through and get into these complexities. But I wanted to bring it up now because Jim, in that training, is going to at least introduce a beta version of MT3D that will work with MODFLOW 6. As of now, without that beta version, there's no contaminant transport capability. So where it leaves us is that all of our old models are in a version that can run contaminant transport, but they're simple. We now have a lot of nice functionality. We can pinch layers out, handle dry cells, this, that, and the other, but we're in a period where we don't have a lot of confidence in the solute transport models. Maybe Jim will change our mind on that, but everything's kind of new there. And as we decide where are we going to go with the big model and what we're doing in Joliet, where are we going to go with East St. Louis, where are we going to go with Green River Lowlands, we probably want to be consistent on all of it, but we need to be able to do contaminant transport with all of it. So I just wanted to run through all of that just so you could have a frame of reference. You don't have to remember all this, but so you can have a frame of reference going into that training about which version. As you go through it, think about which version sounds like the best option for us going forward. The one thing I should point out here before we wrap this up, FlowPy, unlike unstructured grid, which had very little, there's a lot of support for MODFLOW 6 in FlowPy. And I was not brave enough in the class last year when we taught FlowPy to dive into MODFLOW 6 because it was a lot less than that back then. But I'm probably going to try to update it this semester and move everything into MODFLOW 6. That's the way MODFLOW is going. All the developers are working on improving MODFLOW 6 right now. So it's probably 2 splintered paths. Sorab Panday is taking unstructured grid. He's developing it outside of USGS. He's continuing to work on it and improve it. And unstructured grid is splintered off. It's the same people who built Newt. They just splintered off into 2. Like nobody's gonna know this reference. When at the drive-in split into Mars Volta in Sparta, everybody's like, what are you talking about? 90s metal. If you knew 90s metal, you get it. Dan would get it if he was here. Anyway, the team split into 2 directions, and they're each doing their own thing, but this is the one that's supported by USGS, which traditionally is the one that's better vetted, but it's a whole new group now. So we're gonna have to learn some of this the rough way by trial and error. They have to switch back and forth, who knows. But one thing I might recommend after the training is if MODFLOW 6 looks like the way we want to go, maybe we just start trying to move everything over there in the FlowPy realm. But we'll see how that goes. Questions on all this? I'll send out the links to this stuff. Other than that, that's it.
So there exists right now some version.
What's that?
So there exists right now some version of MODFLOW 6 that I can click run on.
Yeah, in Groundwater Vistas, there's a version of MODFLOW 6. So you mean that you can run right now?
Yeah.
Yeah, MODFLOW 6 is operational. So when I started 6 years ago, I was at a conference, and they came out and said, we're 3 months away from unveiling MODFLOW 6. And it's going to give you everything you ever wanted. The way they explained it is you will be able to run any version of MODFLOW. You can choose MODFLOW 88, you can choose MODFLOW 2000, you can choose MODFLOW 2005, NWT, whichever version you want. Any package that's ever been developed, you'll be able to run it. And they'll mix and match. That table that showed which ones behave, they're like, no, those will be compatible. They're going to have all that done in 3 months. 2 years later, they said, we're 3 months away from unveiling MODFLOW 6. But it's completely different. It was all written in, it's what you see now. It doesn't give you everything, it just gives you these options. So you can't recreate the history of any model. So I don't know, they probably spent a year trying to do it and realized, okay, this is a lot harder than we thought. And we went to a training, I think it was 2 years ago, when they actually finally unveiled it, about 4 years later than they originally said they were going to. And it didn't, it was a nightmare. It was all kinds of buggy. So Devin went to the same training after 2 more years, and it's a lot more stable. At least they presented it a lot better. And he has a lot of examples. So he has some example files that you could run. They should have a GitHub page, actually, with some examples. MODFLOW 6, GitHub. Yeah. Assuming there's examples in here somewhere. Updated Python makefile. Oh, that's useful. If you're not running in Windows, you may need a makefile to actually get a MODFLOW executable. we had to use that last year. I mean, you can scroll through here. I don't know how useful this is going to be. Some documentation though, so it's under development, and they said at the last conference they welcome anybody to come in and make whatever change they want. You know, it's on GitHub. They can have a whole version control here. So Avaloki was complaining about something in it, and they said, well, Al, you can change it if you want. Okay, not Al's job, but I'm like, yeah, you can just upload it here. So if you can navigate through this horrible thing, I was expecting it to be a little nicer than this, to be honest, but I guess I shouldn't be surprised. But you can also just go to Groundwater Vistas. You can take the East St. Louis model that's in Groundwater Vistas, and you can just run that in MODFLOW 6. You can just change the properties. I don't know how it'll work, but you know, after probably sometime in November, we're going to start that process with the big model too, just making it run in MODFLOW 6, see what we find, and then slowly migrating it over to FlowPy, assuming we're confident we can get some contaminant transport out of it. But right now, I don't think you'll be able to do any contaminant transport unless we wanted to use something external, make our own, or use something like CrunchFlow. I'm sure you're excited, Cecilia, about CrunchFlow. I don't know. It's an option. I don't really want to go that route. I'd rather wait until they do something official. But there's a lot of options. We just have to figure those out. Yeah, I'd encourage you to just play around with it. Take a model, just run it in MODFLOW 6, see what you see. Then if things are weird, we can always discuss those in these modeling sessions, or just come get me. We can sit down and chat about them too. We'll see where that goes. Okay. Well, that's all I have. So
Thanks, Daniel.
mm-hmm. I'm sorry.
Oh, you're fine.